Okay, welcome back to the Anita and John show. Today I'm going to show you some work that my students are doing, collaboration with John, the golden boy, and our collaborators from Spain. But if you got any questions about it, Anita knows all about this too, so just ask her. She knows it all. But today we're going to talk about radium-thorium ages of single potassium feldspar crystals in alkaline magmas, specifically magmas here in the Canary Islands. This is the island of Tenerife. That's the Las Cañadas caldera. That's El Teide, the volcano the large volcano in the caldera. And we're going to look at a couple flows there, and then I'm going to take you to the bottom of the world, to Mount Erebus, and look at some results from a bomb ejected from Mount Erebus in 2016. So, radium-thorium dating, little background. Radium is compatible with potassium feldspar, thorium is not. So when you've got radium and thorium floating around in a magma, you make some potassium feldspar. The radium is sequestered in the potassium feldspar, the thorium is excluded and remains in the melt. So in effect, what we can do is when that happens, we can calculate crystallization ages really that are a function of the concentration of radium. But in order to calculate this age, we need to determine how much radium it started with, and we calculate what's called a model partition coefficient of radium to figure that out, what that initial concentration is, and the difference between what we measure today and that initial concentration is the age of the crystal. So that's kind of the background. What do we do procedure-wise? We collect samples. We prepare ground mass samples and crystals. The ground mass we basically put under a microscope and pick clean matrix without crystals. And then we sequentially digest them in 1 hour steps of 2% HF, 10, 15 steps. What you get is you dissolve all the fine-grained ground mass and leave any crystals that you missed during the separation process, and you can subtract that from what you started with so you don't have any crystal effects. Then what we do is we use column chromatography to separate out these elements, and we specifically use calcium, barium, and strontium to calculate the D radium using a Onuma curve. The rubidium, uranium, and thorium we use to estimate melt inclusions mostly, or mineral inclusions, and the radium we use to calculate the age. And then we also measure strontium, neodymium, and lead. Strontium and neodymium in this case, typically on the single crystals or the mineral separates. For potassium feldspar, we generate a Onuma curve, figure out what the partition coefficient of radium is, and then we can calculate what the ages of either a single separate or crystal ages, and we all do this all using the Neptune at New Mexico State. So when we determine this calcium, strontium, barium, what we can come and do, since we have the ground mass, the melt, and the crystals, we can calculate partition coefficients for calcium, strontium, barium for every sample we do. We fit a Onuma curve to it, and then where that Onuma curve intersects the ionic radius of radium in the potassium feldspar coordination site, here's where we get our radium partition coefficient, okay? And then, once we know the radium partition coefficient, all we do is go to what we call the radium fan diagram. It's just age versus, age in the past versus concentration of radium. We measure the radium in the potassium feldspar today, in the melt today, right? And then we can mathematically back calculate what those signatures were in the past, and we're showing 1,600 years in the past. But because we have the solid and the melt at any time in the past, we can calculate what the partition coefficient is. And then all we have to do is target the partition coefficient we want. Typically, we ratio radium partition coefficient to the barium partition coefficient, target that at 0.242. If that's what we calculate, then we know that ages of the crystal is 800 years. So that's kind of the procedure. When we go and target samples, we went after 2 different magmas in the Las Cañadas caldera, and then we went and targeted the bomb from the lava lake. They are phonolites. You can see this is Lattice Negras, very clean. That's what a hand sample looks like. Lots of potassium feldspar. And this is a TAS diagram. Phonolites, these are very evolved magmas, both at Erebus and the Canaries. Evolved magma, 60% silica, but very high alkali contents. Okay, and then what are we going after? We're going after the crystals. And you can see these are pictures of crystals from Anorthoclases from the Canary flows, and they're mostly crystal fragments. Might be a couple of intact crystals, but for the most part, they're crystal fragments. And then when we look at the results, this is Lattice Negras, that picture I showed you earlier. This is on the y-axis, the number of crystals. Here it's the age before, age in the past, right? And that is the potassium argon eruption age of Lattice Negras, 800 plus or minus 300, not a very good precision. But then carbon age is a little bit better at 1150 plus or minus 140. What we see is the 5 crystals that look like they give good Onuma curves. And there's some crystals that don't in this flow because they're zoned. But the ones that look like they're not zoned and yield ages between about 1100 and about 1300 years. We assume a 10% error plus or minus 10%. So those ages go right up to eruption, and there's not extensive crystal resonance, maybe a couple hundred years. Looking at the next flow in the Las Cañadas caldera, this is Arenas Blancas. It has a maximum or minimum eruption age of 2,000 years, a maximum stratigraphic age about 6,000 years. And when we analyze potassium feldspars in Arenas Blancas, we see 2 populations. That's what these blue dots are. There's a lower calcium and a higher calcium population of Anorthoclase crystals. And then when we use radium to date them, what we find is Phenocrysts yield about a 4,000 year age. And then there are a bunch of Xenocrysts in here that are dead to radium. They're older than 8,000 years. And because we do calcium both on the probe and here in the isotope dilution for the age calculation, we know that these Phenocrysts fit into that population and these Xenocrysts fit into that population. So now we have some insight on the crystallization history and the distribution of crystals in these rocks themselves. Pretty nifty using radium isotopes. Okay, now if I go down to the bottom of the world in Mount Erebus, here's a bomb that was ejected from the lava lake in 2016. What we're going to do is focus on 17 single Anorthoclase Phenocrysts in here, not the megacryst. Everybody loves the megacryst in Erebus. We don't want the megacryst, right? So let me spend a little time. This is the chemical composition. In this case, it's calcium weight percent, right? And this is the age of the past, and I'm showing you those 17 crystals that we calculated ages on. So these all have radium ages. They range from about 500 years to about 2,500 years. Note there's no ages that are close to the eruption age. And they range in size. So these larger diamonds are crystals greater than 8 milligrams. These smaller crystals are down to about 1.2 milligrams. And we can calculate ages for all those crystals, in this case, in the Erebus magma. So what we see is through this range of crystals, we see pretty tight, 3 to 4%, the bulk of the crystals fall in calcium weight percent. In addition to that, we can look at strontium. We see the same thing from 500 to 2,500 years. Narrow band of strontium, a lot of strontium. And we see it in barium also. And note, there's no higher strontium or higher barium in the younger crystals or the older crystals. That suggests that diffusion is pretty minimal. We've done separate barium diffusion modeling calculations. It's also indicated that radium is probably not affected by a diffusion here because we don't see it in radium. Radium's going to diffuse a lot slower than barium in Anorthoclase. So then we look at the 87-86 ratios. Here's the ground mass. Most of these crystals fall into the range, maybe a little bit higher in 87, 86, but pretty similar, which should suggest through time Erebus hasn't changed in 87, 86, and it's probably pretty close to equilibrium. Here's the big peaks of lead. Big peaks of lead. Here's the ground mass again. Most of those are a little bit higher than the ground mass value. There's one crystal that drops lower, but most of them cluster in the same range. When we look at a little bit more detail with the 206, 204 lead, you see more overlap here, but again, pretty similar to the ground mass. And we would suggest this indicates equilibrium between the melt today and these crystals, because the melt hasn't changed very much. And then if we plot our D-radium, D-barium ratio through time, we also see that this ratio hasn't changed very much. As a result, we think it's one, accurate, and two, we use that to recalculate Mark Regan's 1992 evaluations of the megacrysts. And where do the megacrysts fall? Between about 2,400 and 2,700 years out here, assuming it had the same ratio as the Phenocrysts. So, conclusions. The Ramos et al. 2019 model that estimates the D-radium, D-barium apparently works. We can effectively date crystals that formed immediately prior to eruption and older crystals. In the Canaries, we have those crystals that look like they formed probably within 300 years of eruption. But in another flow, we identify both Phenocrysts at 4,000 years and radium dead crystals to understand the petrology of these rocks. Mount Erebus, we get a wide range of ages from 5 to 2,500 years with minimal suggestion of diffusional re-equilibration. So at this point, we are ready to work this technique. Let's start figuring out what's going on with these magmas, what's causing eruptions. And so with that, Anita and John are great. Here's John in Barcelona with myself and Al and On. And then here's Anita in South Africa beating on a rock. And I want to tell both of them, thanks for being my colleagues and thank you for being my friends. Thank you very much.